everyone. We're very punctual here in the Science Institute. I'm Shafi Golosa, the director of the Institute. And I would like to welcome all of you. I think I know many of you, but not all. And just a word about the Institute. We're an Institute for Collaboration and Peer Computation. We've been around since 2013. And as you know, we hold semester programs, clusters, workshops, all centered around peer computing and its relations to sciences, mathematics, and engineering, and sometimes social sciences. And I'm not going to say more words than that. All I want to say is that I want to welcome everybody to this very special occasion, which is Mickey's not exactly birthday, but a retirement party. And I think there's no one better than that to celebrate in a place like this, which is dedicated to peer computing, because he's done so many fundamental works which have been cornerstones in our field. And I hope that today we're going to find out about a lot of them and what has happened through the years and the impact that it's had. So congratulations, Mickey, for an amazing career and amazing contribution to the theory of computing. I'm going to give you a round of applause. Who is a student in Pekin.
Okay, so as Shafi said, thank you, Shafi. Thanks a lot for the hosting of this event, and we're very happy to see all family, almost family, friends, and colleagues and dear people. So we're having this celebration in honor of Michael Benor, Mickey, for me. After a long time of basically, it was supposed to be maybe 8 years ago, and then all the titles are already gone. So now it's without any title, just a celebration of Michael Benor's amazing work. And where is our first speaker? Here you are. Okay, so I don't think I need to do anything except for invite Avi to talk.
Okay, thank you. I first echo everything that was said, Mickey. It's great to be here and great to celebrate your whatever it's called. I guess is a naming problem, but celebration. So for those who don't know, Mickey and I go back, I guess, 40 years. Yeah, we met about 40 years ago, and then I came to the Hebrew University a year or two after he got there. And he was the main attraction for me, obviously. And I don't know how many of you know Mickey. I'm not going to tell too many embarrassing stories because I want to show him something that he would like. But my office was at the end of the corridor of this, at the time, small department. And Mickey was 2 doors next to me. And I passed there every day, many times. Mickey's door was always open. And Mickey, you would say he seemed to have all the time in the world, but he didn't seem to have it. He had it. He has all the time in the world and all the patience in the world. And whenever you pass by his office, you strike a conversation, and then he would tell you something you didn't know and will explain it in whatever amazing clarity and detail. And I don't know how much I learned just by passing next to his door. And so we had 15 years roughly together there. We wrote only 3 joint papers, but boy, what papers. We had 3 joint students, but boy, what students. Dorit is one example here. So I want to just say a few words before getting technical, because the only person I have to entertain is Mickey. Just a list of some of the areas to which Mickey has made really amazing fundamental contributions. But to me, a lot of it is, the gems, the ideas that go into this contribution. I'm not going to go into any detail except the last one. Very early on in asynchronous Byzantine agreement, there was an impossibility result. And Mickey said, well, we can do it nevertheless, just use randomness. This is in the really early 80s, one of the major demonstrations of power. Distributed computation, we have this joint paper that many of you know about how to do joint computation in information theoretic setting. Analysis of Boolean function, maybe, I don't know if Nati will talk about it or maybe not, but there was the most influential paper on influences, which started this analysis of Boolean functions. Interactive proofs, this one of our joint paper with Shafi. Joe Killian is the one introducing the extra prover, what's called today many prover interactive proof systems, and many people took it from there to amazing places, including this MIP star equal RE results a couple of years ago. Just, yeah, incredible. So I want to talk about very recent work and stuff that Mickey did actually in his PhD thesis. And afterwards, before he moved to quantum computing, where he also, of course, used this knowledge, is the recent joint work with a postdoc of mine at the Institute, Robert Andrews. And I want to talk about parallel algorithms for linear and polynomial algebra, which I know is one of Mickey's love. Yeah, now I'm getting technical. It's all very simple, right? So don't worry. Models, the model of computing in arithmetic is, if you're used to Boolean, you just replace and or with plus and times, right? So when you compute with plus and times over some field, let's fix a field, then you are computing polynomials. We'll stick to polynomials whose degree is roughly the number of variables, multivariate polynomials. And we want efficient computation. So we want polynomial time computation. So that's a model, one for every field. And we want to understand what's easy and what's hard in this arithmetic computation. And very early on, complexity theory existed like 2,000 to 3,000 years ago. People were interested in efficient algorithms always. And one such example of an arithmetic computation with plus and times and maybe divide is the Euclidean algorithm. Of course, Euclid talked about GCD of numbers, how to compute a common divisor without factoring. This was very important. Already then they realized that factoring is difficult. So nevertheless, this is an efficient computation, computing the greatest common divisor. Here, of course, it seems like a GCD of univariate polynomials, but of course the inputs are the coefficients of the polynomial. So that's what we are really computing is the coefficients of the GCD. So that's multivariate computation. Anyway, that's efficient, as we all know. Here's another thing that you all know, Gaussian elimination. It existed lots before Gauss. I mean, even in ancient Chinese texts, there are descriptions of this algorithm, although without proof, but Egyptians did similar things. Anyway, the determinant of a matrix can be computed easily, as you all know, from school or college. And there, of course, once we needed them, once computers came, lots more efficient algorithms in this setting, in this arithmetic algebraic setting, were invented. And then came the 60s and 70s, and everybody, there was parallel architectures and distributed architectures. People want to do everything fast in parallel, maybe with many processors, many computers. What can you do? This GCD, you all know how it works, right? So you divide one polynomial by the other and take the remainder and replace, and then if the degree on polynomials, maybe 10 steps. So it's efficient, but not in parallel. Gaussian elimination, again, so you eliminate a variable, it goes down one row. If you have an n by n matrix, it may take you n steps. Can you do it with many computers in parallel? It seems inherently sequential somehow. So what happens? Well, first let's explain what parallel means. It means that you want not just a small circuit, but a shallow circuit. this will capture the parallel time because each layer you can compute at once in many processes. So it's another class besides P. These are the NC classes. You want to say the problem is in NCI if it can be computed in log n to the I depth, like log n depth, log n squared depth. And we have this chain of inclusions, which is the obvious one. On the right-hand side is polynomial size. On the left-hand side, NC1, what you can do in log depth, you can actually do with polynomial size formulas, which is a model that's very natural in math. Which problems have fast parallel algorithms? In particular, can we do GCD or the determinant? Anybody knows? I'll tell you, don't worry. Shortly after these questions were asked, people answered them big time. There was really a golden decade there, same golden decade as with cryptography, I would say, where results started pouring in. So it looks like it's very hard to parallelize these problems, but then Sansky found this, at the end, really simple, but very surprising algorithm. Says determinant, you don't have to eliminate some things one at a time. You can do it in parallel. In fact, log n squared depth is all you need. That was one surprise. And with this came, of course, determinant is central to linear algebra, and then many other related problems were solved fast in parallel. Matrix inversion, linear system solving, computing the rank, which is not trivial, doesn't follow from determinant, so on. All of linear algebra fell into NC2. What about something that looks different, like the GCD? Well, it's really, when you phrase it correctly, it is linear algebra. You can set up a linear system that will get you the GCD. So this was done. And then, okay, so these linear algebra problems have fast parallel algorithms, but then something amazing was noticed, first by Hiafil, and sort of clarified a little later by Valiant Align, but Hiafil said, forget linear algebra, forget anything. If you have something that can be computed efficiently, it can be computed efficiently in parallel. Can be done, you can reduce the depth and do it in parallel. So it includes all these other results as corollaries. So it's pretty amazing. And this was more or less the culmination of this golden decade. And okay, that's where it stands, and it's implemented everywhere and so on. But basic questions remain. What can you do it faster? In particular, can you do polynomial size formulas or reduce to log n depth? Or maybe you can do it in constant depth, in constant parallel time. Okay, so let's see what to do about this. I just want to again show you the model. I started it 15 minutes ago. Okay, good. Yeah. I'll finish on time.
10 minutes, already 11 minutes.
I think we're very flexible here in honor.
Yeah, we can talk about how much time I have allotted. So, how can you do anything in constant parallel time? Well, you allow the operations to be not a binary fan-in, but you allow to add many numbers at once, or multiply many numbers at once, like in this picture. So you have this polynomial, and I have two circuits for it of depth 2. One, of course, is extremely expensive. You just add up the monomials, but there are exponentially many. That's not a good one. In the bottom, if you just multiply, just like it's written over there, then you see that you can do it in polynomial size. So that will capture for us this class AC0, the class of anything that can be computed by a polynomial size circuit and constant depth, independent of the number of inputs. This is as best as you can hope for. Nothing, faster in parallel or efficient that you can have if you don't bother about the exact polynomial size. So what's in this class? It seems extremely weak. So that's how the status In fact, it looks like up to a couple of years ago, we didn't even know that any inclusion there is true. Amazing. So what's in this class? There are still things you can easily do. Here are problems with univariate polynomials that you can solve. You can take two polynomials and add them. I mean, you just in parallel add the coefficients. You can multiply, it's a convolution, but that's still, it's easy. You can evaluate a polynomial because you can add many things at once. You can interpolate the coefficients of a polynomial from its value. That's a linear addition. Some more non-trivial things came up, like division with remainder is not obvious. It's far from obvious, but Fan and Bineri showed that this can be done in this class.
This is integer.
But no, nothing is integer. Everything is polynomial. I should have remarked, thank you, that integer case is a very different thing. Two ways to see it, GCD of integers is believed to be impossible to parallelize. And moreover, this depth reduction that I showed, that everything that can be done in polynomial size can be done in shallow depth, nobody believes it in the Boolean world, in the integer world. Yeah, so it's all polynomials, and that's the setting I'm talking about. Yeah, but this can be done. Another thing that can be done is another gem of Mickey's, one of his earliest gem, and one of the first things he told me when I arrived to the Hebrew University. And I never did anything with arithmetic computation before, and I fell in love with the subject immediately. So the elementary symmetric polynomials, you can define here, and you all know basically this is the symmetric polynomial. Let's say that this symmetric polynomial, you basically sum up all monomials of multilinear monomials of size d, an exponential number of them. This is a elementary symmetric polynomial that play a fundamental role. I'll talk about it in a second. And it seems like it's another thing that you cannot do in parallel at all. And Mickey's gem was not only can you do it in parallel, you can do it in parallel in depth 3 and size n squared as a formula. And yeah, I was blown away by this. I think that Mickey never wrote it up. Did you? But everybody cites him. Yeah, so here, let me show it to you. I mean, how do you do this exponential number of monomials? I mean, the answer is on the board somewhere because on the slide. So let's set up a new univariate polynomial. I mean, these are multivariate polynomials. Set up a univariate polynomial in a new variable z, which will be the product of 1 plus z xi, right, for variable x, and expand it. And when you expand it, you see that as a polynomial in the new variable z, the coefficients are simply the elementary symmetric polynomial. Okay, so in depth 2, we can set up this polynomial and evaluate it. Let's evaluate it at n plus 1 point and interpolate one more layer. Yeah, I'm still blown away, and I love teaching this. Yeah. Okay, so we know that, and that's a non-trivial thing we can do in AC0, and what I want to do in the rest of the time is explore what more. First of all, we have to know, are there limits? And as I said, it's amazing. Up to 2 years ago, we had no limits on AC0. We know in the Boolean setting, we had lower bounds from the 80s. We knew that constant parallel time, you cannot do the most trivial things, like the majority function. But majority is really the elementary symmetric polynomial. So why couldn't we do it? Well, I don't know why we couldn't. We should have. But anyway, finally, this breakthrough of Reminiscing, Wigderson, and Tabernas came, and in particular, one of the problems we are really interested in, or linear algebra, the determinant cannot be done. There are more. I'm not going to talk about that. But the other problem we talked about is GCD, polynomial GCD. And I want to show you that this is in AC0. You can do it in constant parallel time. So I'll explain this maybe, I mean, if you asked me before 2 months ago, I would say that's impossible. I'll just say that there is lots more that we can do, but in particular, lots of things that are related to the GCD, like the resultant, which tells you whether the GCD of whether two polynomials have a common factor, discriminant, the coefficient of the resulting GCD, and others. Actually, we can do it not just for two polynomials, but for any number of polynomials. And I'll show you how. Questions so far? Okay. So it all has to do with symmetric functions in the root of a given polynomial. So, you know, you have a polynomial, a univariate polynomial given by its coefficients, then you can at least imagine over the algebraic closure that it factors completely. These roots may not be in the field you are in, maybe they're in the closure, you don't know them, but but it exists, such a factorization exists. So the roots are there. And then you have to realize, which I'm sure most of you know, that in terms of the roots, the coefficients of the polynomial are the elementary symmetric polynomials in the roots. So f sub d, the coefficient of x to the d, is these elementary symmetric polynomials in these numbers, r sub I. And even though they may lie in some extension field, this value will be in your field. So what we are given, when we are given a univariate polynomial, we are really given all the elementary symmetric polynomials in its root. That's a message. And what can you do with this message? Well, you have these symmetric polynomials, and they are all you need, really. There is a fundamental theorem of symmetric polynomials saying that if you have them, these elementary ones, you can compute any other symmetric polynomial as a polynomial applied to them. So you can ask about other symmetric polynomials, and one particular one that we like is power sums. It's even simpler than elements. You just want to sum the case power of the variables or of the root of the variables. So we don't just care about computing things, we want to compute them really fast in parallel. What can we do about this? Well, we have the Newton identities, which are called Newton identities, even though Girard discovered them a little earlier independently, I assume. Anyway, but Newton also discovered them independently. You probably have never seen it written like this, but another message is that the power sums are really the logarithms of the elementary symmetric ones. I can write down a formula, I will not do it, but you'll see an application and you'll understand why I'm saying it. And it turns out this is really folklore. I think that people knew, certainly Amir Spilka and I used it in the 90s and maybe earlier. You can converse between these two representations of the roots, right? The elementary symmetric ones or the power sums of all the roots in AC0. And this is an extremely powerful thing. And let me show you a demonstration. So we'll see what other things you can do later, but let me just show you the power of this logarithmic thing. We were inspired by this paper, which is not about parallel computation, but they do some cool things with this transformation. So here, example, let me use this notation that the power sums of f are really the power sums of the roots of f. Okay, take care of f. Let's look at the problem of exact division. Two promise problems. One promise problem, I give you two univariate polynomials, and I tell you d divides h. Compute the ratio. It's a polynomial. Well, the power sums of f over d, this is the logarithm thing. It converts multiplication to sum, division to subtraction. Power sums of f over d is the difference between the power sums of f from the power sums of g. So convert to power sums, do this trivial thing, convert back, you are done. Similarly, you want to take the root of a perfect power. I give you a polynomial, I promise you that it's the dth power of some other polynomial, h. You want to find x? Well, take the power sums of h and divide by d. It's an amazingly powerful thing. So that will be an engine hiding in everything we do. There'll be more, but these are the basics. Yeah, that's the infrastructure. So what more can you do? Well, here's two polynomials given. Let's say the f again has this decomposition. I want to show you trivial things that again will be the basis of the GCD, and you can given the power sums, you can easily sum up this polynomial over the roots. The power sums are just a polynomial x to the k, and you sum it over the roots. Any polynomial you can sum over the roots. That's one thing. Sum is not as interesting as a product, for example. If you manage to multiply each of the roots, then you'll get the resultant, this thing that tells you about GCDs very quickly. So can you do products? Well, in fact, you can do all elementary symmetric polynomials in the roots. That will be another key thing. So the last elementary symmetric polynomial is the product, right? So in particular, you get this, but you get even more. Maybe some of them are zeros, and you want just the products of the non-zero ones. Well, I mean, whenever you have an elementary symmetric polynomials of some vector, and you want just the product of the non-zeros, it will be the last non-zero elementary symmetric polynomial. So if you didn't follow this, don't worry, it's a bit technical. But it's just, you can do the product of the non-zero part of any vector. Okay, so now I'm back to GCD, and there are two more slides. I want to show you how you can filter. So now you have two polynomials. It's not just symmetric polynomials you can compute. You can compute some symmetric polynomials in the Venn diagrams of the roots. So here are two polynomials. Let's say that I'll do only the multilinear case. So there are no square factors to any of them. If R1 through R sub m are all the roots, let's say that f of x is the product of the first n, and g of x is the product of whatever, the last one, and there's some intersection. That's the GCD is after computing the product of the x minus ri in the intersection. Right? That's what we want. Okay, how do we do that? Well, so that's why I'll compute this part of f, and then of course we can divide by it to get the GCD. Now remind you, we don't know what the roots are. We don't know what k is, how many things they share and how many they don't. We don't know this. We just know the degree. We set up this filter. I mean, it's really, I think of it as a filter, this extra polynomial, h of x and another variable, new variable y. And it's g of x, the one of these two polynomials, and times y minus x. Y minus x because, or y g of x. G of x will be 0 on the root of f, on the root, sorry, of g, right? When you feed it a root of g, it will be 0. And that's how it will filter for us everything we don't know that. That's what it is. And we know that, for I greater than k, wherever we are not interested, it will become 0. It's a root of g. And the way we use it, I just told you in the previous slide, if you have all the elementary symmetric polynomials in h, this h, of R1y, R2y, and so on, it will be 0 beyond k. And since the elementary symmetric polynomials tell us the last non-zero one tells us a product, we get this product, exactly what we are after, times something, but this is a constant. It's just a product of g evaluated at some number. So up to this constant, we get not the GCD. For the GCD, we just divide f by what we get. So this is it. Using this filter, you can get the GCD. So what more can you get? And now that's good. The general case, you don't really have the product of x minus ri. You have these multiplicities of roots. What do you do with them? Well, you do what you did before. There are some more complications because you need derivatives in the filters, but I'm not going to go into this. just want to point out, as a function of the roots, what kind of function is it? What are we doing? Well, the GCD is really the product of x minus a root to the power of the minimum of the two multiplicities, right? Okay, so we can compute this type of function of the multiplicity. The largest common multiple is the same, only you have max. There are other functions we can put there and do it in AC0. There's a trivial one. If we multiply two polynomials, then in the exponent we get a sum. And you look at this and say, okay, what other functions of the multiplicities can you put there? For example, can you multiply the exponent? Nati, what do you think? No. Is it even algebraic? You can. It's really weird. I mean, what kind of operation even is it? You multiply the exponents, it doesn't make sense. But actually, whatever you put there, you can compute. It's algebraic, and it's even an AC0. As I said, we can do GCD of many polynomials, and also for them we have you can do many more things with the exponents. That I think I'm not going to talk about this. Let me conclude here. Put my favorite slide on my last slide on the board, and congratulate Mickey again. Thank you.
I don't know if we do questions in this, but let's take one.
No, let's do only answer.
Just answer, please.
Yes, yes.
Second on integers? You said so.
Yeah, so the integer is basically a different story. There are carries in integers. I mean,
Tell me about this.
yeah, I mean, tell me about it. Yeah, exactly. No, it's really a different word. I should point out that if you want to, an analogy to the integers, remove this variant restriction. So we, for 30 years or 40 years, we are doing arithmetic complexity, assuming that the polynomials we are computing have polynomial degree. Because these are most polynomials we care about, and it's natural. But in polynomial size, you can compute polynomials of exponential degree. You can repeatedly square n times. So, okay, I know that, but what do I do with it? If you want to think about integers, think of removing the restriction, allowing any degree. Then you don't have this parallelization of every algorithm. Then you don't have a lot of things. This would be a good analogy.
No, it's an easier analogy because you can prove the things.
Also. In general, many things are easier in terms of hardness results in the arithmetic setting, except this AC0 lower bound that was discovered only 30 years after the Boolean case.
Okay.
Thanks.
Thank you, Avi. And Pat was also a pure student